Thank you very much for the introduction. And okay, I'd like to thank the organizers for inviting me and giving me such a great chance to give a talk today. So I'm going to talk about my recent paper on cluster algebras and monotone Lagrangian tori, and which is joint work with Myung-ho Kim, Yuji Kim, and Yunhyung Park. Okay, first, I'd like to talk about the contents of this talk. So this talk is about the so-called monotone Lagrangian tori, which is very important object in the study of symplectic geometry, and which only lives in smooth Fano variety in algebraic case. And this talk is about monotone Lagrangian tori living in a smooth Fano variety, which is birational to a cluster variety. For instance, the compactification of a cluster variety. So other notions that I will explain later, and I focus on two subjects. So how to construct a monotone Lagrangian tori, and I will use the toric degeneration, which has already appeared in Harada's talk. And there are two kinds of as far as I know, there are mainly two ways of producing toric degeneration. One is Grobner degeneration using triple geometry, and the other one is using theory of Newton-Okunko bodies. And also, for the constructed monotone Lagrangian tori, I will explain how to distinguish them. And then to do that, I will use so-called Gromov-Witten invariant for the disk. Okay. So, so this is about why we study monotone Lagrangian torus or monotone Lagrangian submanifold. And the first one is the theory becomes beautiful. So there's no obstruction to establish some infinite dimensional world theory or something. And also existence of monotone Lagrangian torus characterize the Fano variety. Then meaning that if there exists a monotone Lagrangian submanifold in a projective variety, smooth projective variety, then that variety should be Fano. So in that sense, it characterizes the Fano condition. And also there is a context of mirror symmetry of Fano variety. The one thing is there's a theory of counting closed curves. For instance, rational curves or spheres or some Riemann surface with a higher genus. And then there's another story. It's about the counting disks. So we call open curve. And to count the disks, we need a certain Lagrangian boundary condition. And in this case, monotone Lagrangian plays an important role in the theory. So, okay, now I start. So to define a monotone Lagrangian submanifold, we should recall what a Maslov index is. Maslov index is a homomorphism from the group of group pi 2, the relative homotopy group, which is nothing but the homotopy class of disk whose boundary is lying on the Lagrangian L, and it assigns to a certain integer. So it is defined as follows. So pick a certain disk class, and then it can be represented by a continuous map from the two disk D to X, whose boundary round D to L. And then we pull back the tangent bundle of X along U, and then we can choose a trivialization because D is contractible. So it is isomorphic to D times Cn, where n is a complex dimension of X. And then we restrict the continuous map U to the boundary DL because DL goes to L. So we also pull back the tangent bundle of L along this map. Then it becomes a certain Rn bundle over round D and living in the trivialization D times Cn. So in this picture, the round D parameterize certain Lagrangian subspace inside of Cn, which is the loop in the Lagrangian-Grassmannian. So the Maslow index is defined by as the degree of the composition, the determinant square, and the map from round D to the Lagrangian-Grassmannian. So intuitively, it measures how the Lagrangian twist along the round D. Yeah. Which depends on L as well as the map U. Yes. Yeah, actually, it depends on the homotopy class of the disk. So that this the mu Maslow index is well defined. Okay. And it respects the addition. Okay. All right. So in particular, when L is orientable Lagrangian, then the Lagrangian-Grassmannian becomes UN mod of SON. So determinant map is well defined. So in that case, the degree always becomes even number. Right. So here's the most simplistic example. When X is a C and the Lagrangian is a circle, and then if you want to compute the Maslow index, then also at a glance, along the circle, the Lagrangian subspace twisted twice, right? Line twist twice. So you can see that immediately check that the Maslow index is 2. And more generally, if we consider a map from the two disk to n times a unit circle inside of Cn, which is called the Clifford torus, and you map C to C dot dot Z k times, and the other is fixed by 1. And you can easily check that this disk has a Maslow index 2k. So here is some convenient way of computing Maslow index using Hamiltonian S1 action. So if we have a symplectic manifold, 2n-dimensional symplectic manifold, and if we have a Lagrangian L, which is S1 invariant, and it is lying on some level set of, the level set of the moment map, and take a free orbit of S1, and then we take the gradient flow of the moment map with respect to certain S1 invariant compatible almost complex structure. And then the S1 orbit goes to converges to some fixed point, right? And then we compute the weight of the fixed point, and then the Maslow index of the corresponding disk becomes twice the number of negative weights. So for instance, in toric picture, if we consider P1 times P1, we consider the generic Lagrangian torus fiber. And then whenever we choose a direction, rational direction or integral direction, then we get a circle action. So for instance, if we choose -1, 0, the direction, that it generates a circle action whose fixed point, whose maximal fixed point becomes a sphere corresponding to leftmost edge. And then you can immediately compute that the weight at the maximum is 0 minus 1. So in that case, that disk has Maslow index 2. And also, if we take a direction -1, 1, and then at this time, the maximal fixed component becomes isolated fixed point. And then you can see that the weight is -1, -1, so that this disk has Maslow index 4. Okay. So there is a famous theorem by Cheol-hyun Cho, not me. So it is a kind of classification result of Maslow index 2 disk. I will explain later why we we should care about the mass flow index to disk. So the theorem states as follows. If L is a torus fiber on a compact symplectic toric manifold, then there is a one-to-one correspondence between the mass flow index to disk bounded by the Lagrangian torus fiber L and the facets of P. The correspondence exactly described in the previous example. And the theorem tells us that that's all mass flow index to disk up to a certain equivalent condition. So far, we defined the mass flow index, and now I will explain what a monotone Lagrangian is. Okay, you can ignore the last part. So, okay, recall that so symplectic manifold is called a monotone if the symplectic class is the Chern class is positively proportional to symplectic class for some fixed lambda. That means that considering a pair with a curved class, that means that every symplectic area of a surface is positively proportional to the Chern number. Okay, so the mass flow class is kind of relative version of this Chern number. So we say that a Lagrangian is monotone if the mass flow index is positively proportional to the symplectic area for some fixed delta. So I will explain the example using example later. So here's the easy theorem. So every smooth Fano variety is monotone because the anticanonical divisor gives Kodaira embedding, and its pullback becomes Keller form. And then if X is simply connected projective variety, smooth projective variety, and L is monotone, if there is a monotone Lagrangian submanifold, then X should be Fano. And in this case, delta is twice lambda. So two monotonicity constants should be related to each other. So here's a baby example for the sphere. We know that if omega fs is the Fubini study form on P1, and then we consider its volume is 1, and then you see that the Chern class is twice the symplectic class because Chern number is 2. But for the equator as a Lagrangian, the D plus and D minus has both area 1/2, but they have mass flow index 2. You can easily check that. And then you will see that it is 4 times area 1/2, and it becomes a mass flow index. So in this case, yes?
Just to remind us what a Fano variety is.
Fano variety is anticanonical divisor is ample. So, or more conveniently, if the pairing the first Chern class, if we have first Chern class and any algebraic curve, the pairing should be always positive. Yes, that's the same condition. Okay. So let me explain by example toric Fano variety. You know that toric Fano variety is in one-to-one correspondence with reflexive polytope. Now, you know the reflexive polytope is a lattice polytope whose polar dual is also lattice polytope. And for each dimension, there are only finitely many reflexive polytopes. So the classification of the Fano variety is very important. And we can say more generally, there are one-to-one correspondence between toric Q Fano variety. Q Fano means actually Q Gorenstein Fano, but the Q Fano means actually the anticanonical divisor is Q Cartier, Q Gorenstein. Anticanonical divisor is Q Cartier. So multiplying certain integer, it becomes a Cartier divisor. And then the corresponding combinatorial object is so-called the dual Fano polytope or Fano polytope, where the Fano polytope is defined very easily as follows. So Fano polytope is a lattice polytope such that the origin is in the interior, and every vertex is primitive integral vector. So it is very easy, but in general, its dual is not necessarily a lattice polytope. When it becomes a lattice polytope, then it is a reflexive polytope. But in general, it is not true. So here's an example. So, it's already a little bit shifted, but anyway. So the first example is the typical example for P2. So this is an example of reflexive polytope. And the second one is the moment map for the P114 as a weighted projective space. And it is actually in N side. The Fano polytope, actually the Fano polytope lives in N side and dual Fano polytope lives in M side. So moment polytope lives in M side, right? So the moment map EBC is a rightmost one, which is not obviously not a lattice polytope. Okay. So here's the theorem. Every smooth toric Fano variety has a monotone Lagrangian torus. Actually, there is a unique monotone Lagrangian torus fiber. You know that sorry. And previously, the Fano polytope, actually, you can easily see that on the dual Fano polytope, it has an origin in its interior, and it is a center in the sense that the distance, affine distance between the center to each facet is always 1. So dual Fano polytope is, in other words, it is a polytope with a center. So the location where a monotone Lagrangian torus fiber is actually the center. So the prop is as follows. So if we denote L0, a fiber at 0, and its facet can be expressed by this formula where A1 to AN is a vertex of a Fano polytope. And so, by the way, the Maslov 2 disk is called the basic disk. So each basic disk is of Maslov index 2, as we saw before. And it has area 1 because the affine distance is 1. So the ratio of the symplectic area and Maslov index is always 1 to 2. So it is a monotone Lagrangian. And this is the toric Fano case. And it is a long-standing conjecture that every smooth, but not necessarily toric, Fano variety has a monotone Lagrangian torus. So actually, it turned out by Dmitry Tonkonov that this conjecture is equivalently saying that existence of Landau-Ginzburg model for smooth Fano varieties. But I will not explain what a Landau-Ginzburg model, but you can imagine that it is it gives a certain generating function of closed curve counting. Sorry, Gromov-Pittin invariant. Okay. Okay. Yeah.
Could you explain that connection with mirror symmetry there?
Okay. So I will explain later, but if we have a monotone Lagrangian, then I will construct certain theory of counting disks. And then the mirror symmetry of Fano variety in algebraic side, they establish certain theory of counting closed curves. And mirror symmetry expect that one can recover another and vice versa. So actually, Landau-Ginzburg model is for the algebraic side, and monotone Lagrangian model is about the symplectic side. So now I will explain how to distinguish Lagrangian. Suppose that we have two monotone Lagrangians, and then there is a notion of equivalence between them. So we say that two Lagrangians are equivalent. Actually, there are two notions, but in simply connected case, I will treat them equal. But anyway, there is a certain isotopy called a symplectic isotopy or a Hamiltonian isotopy, such that the time of map sends one to another. So this gives an equivalent relation between Lagrangians. So then the question is, so how to distinguish them? So we have a L and L1, then what's the invariant of the symplectic or Hamiltonian isotopy? Then the answer is, as far as I know, except for a trivial answer like a topological type or something, the non-trivial answer would be the disk counting invariant. So this is kind of called the open Gromov-Witten invariant, and something like this. So it will not used later. So I just briefly say that. So for each Lagrangian, so we can consider the moduli space of a holomorphic disk for the choice of enormous complex structure. And if we fix disk class beta, and then we construct a moduli space mx beta, which is a J holomorphic disk with a Lagrangian boundary condition, and the class is beta. And modulo certain the equivalence, I mean the transformation of the disk, automorphism of disk. And then it turned out that its dimension is n-3 plus Maslow index of beta. And if we put one marked point on the boundary, then something like m1 x beta is kind of s1 times mx beta, something like that, or locally. Then its dimension is bigger than 1, bigger than m, bigger by 1 than m. So its dimension becomes m-2 plus Maslow index of beta. And when Maslow index of beta is 2, then the dimension of m1 becomes n. So the evaluation map sends an n-dimensional space to an n-dimensional space. So we can consider its degree. So the degree of evaluation map is intuitively the number of J holomorphic disks with the boundary condition passing through a generic point. So it gives a certain counting invariant of Lagrangian. So I said I will explain why we should care about Maslow index to disk, because it gives a counting, I mean the degree of evaluation map. Otherwise, degree becomes 0. Okay. All right. So now for a monotone Lagrangian torus, we define certain low-rank polynomial, which is called the potential function for the Lagrangian. It is given by the summation of n beta z sub round beta, where n beta is a number of disk of class beta, and round beta is the boundary class of beta in H1L Z, which is isomorphic to Zn. So here I used the exponent notation. And of course, this expression depends on the choice of basis of H1. And we regard the two expressions are same. And then this Laurent polynomial also gives an invariant of L. So if they are not equivalent, then two Lagrangian tori are not isotopic. Okay, so in tori case, it is there's a because Maslow 2 disk is classified, then we can easily check that the potential function of the monotone Lagrangian of toric Fano variety is of this form. We just look up facets and its normal vector, and then compute. Right. Now I will explain how to construct the monotone Lagrangian tori. So actually, I will use toric degeneration of a toric projective variety. So as we have seen in Harada's talk, toric degeneration is flat family of variety in Pn, and it is a flat family over C such that outside of 0, it is a trivial family. I mean, the pi inverse C star is isomorphic to X times C star, and the central fiber X0 is an irreducible toric variety. So here's some non-trivial example. If we have a flag variety, then it has a Plucker embedding to P2 times P2. So by dimensional reason, we have one relation. So the relation is given by the three-term polynomial. And then toric degeneration is something like that. So when we plug T0, then it becomes toric variety associated to so-called Gelfand-Zetlin polytope. And then, so as T goes to 0, the flag variety converges to a toric variety. Actually, in this case, some vanishing cycle is S3, and it goes some singular point of toric variety. So here is the certain easy criterion that suppose we have a smooth Fano variety, and so the assumption is that if we have a toric degeneration where the central fiber is normal and Q Greenstein Fano or just Q Fano, then we can find the monotone Lagrangian torus in X. So the proof highly use the theorem of Harada and Kabe, where their theorem states that whenever we have a toric degeneration, then there is a continuous map from the generic fiber to a central fiber, which is symplectomorphic almost everywhere, so that we can pull back certain symplectic information of X0 to original space X. So, So we will use that continuous map, and the normality implies that the singular locus of X0 has codimension greater than or equal to 2. So the smooth part contains interior of a polytope as well as interior of a facet. And as we saw before, the basic disk or master index 2 disk are living in the interior of a polytope and interior of a facet. So it is preserved. So pictorially, so when X0 is of that shape, then ignoring codimension greater than or equal to facets, then the shape is living in X similarly. So we can check the monotonicity of Lagrangian using that basic disk. So in conclusion, to construct a monotone Lagrangian torus, it is enough to construct a normal Q Greenstein Fano toric degeneration. So that's the conclusion. And okay,
So in some sense, you're pulling the information back from the toric degeneration. Are you getting the structure?
yes, I will pulling back the information of toric variety to an original variety. Yes, yes. So one example, as in Harada's talks, so we can construct a toric degeneration via Newton-Kunkov body. So actually, this is a basic concept of Newton-Kunkov body, but okay, all right. So usually for a projective variety and a prime divisor D, we can define a valuation on its function field. And actually, it is defined as an order of vanishing of a rational function on D. So namely, because D is a prime divisor, locally D is defined by one equation G, and then also locally, the F can be written as G to the K and H, where H is non-vanishing on D, and then K becomes a valuation of F. So this is an easy example. So, and then more generally, if we have a flag of subvarieties, varieties, then one can construct a valuation associated with that flag, where the value is in Zn, inductively as follows. First, we record the order of vanishing on V1, and we erase the vanishing part, and then we record the order of vanishing of Y2 of the remaining rational functions, and so on. All right. So using this construction, we may equip a valuation. We may restrict our valuation to a coordinate ring, and then certain recording is level. Then we have a extended valuation, and that the image becomes a semigroup, affine semigroup is called a valuation semigroup. And then if this semigroup is finitely generated, then there exists a toric degeneration of X to a toric variety, proj of the semigroup algebra, and whose moment polytope is actually given like this. It is called the Newton-Okonkov body for the flag Y. So using this theorem, we can see that the central fiber is projective normal if the semigroup is saturated. Oh, sorry, these S is saturated, and therefore the central fiber becomes normal. So to get a normal toric degeneration, we should look up carefully the semigroup. Okay. Now I will explain how the theory of cluster algebra comes in. So we recall that cluster algebra is a C algebra generated by seed, where a seed is a pair, X and epsilon, and X is a certain n variables, which is algebraically independent, and epsilon is an n by n matrix, integer matrix, which is skew symmetric. Actually, if you are familiar with cluster algebra, I will ignore some frozen variable part. So our variable is called the cluster variables, and this matrix is called the exchange matrix. And for each k from 1 to n, we can produce another seed. It is called a mutation, which I denote by mu k. So if we plug S to mu k, then there becomes another seed, S prime. And the formula is given as follows, but it is not important. But the important thing is this formula is written as a certain rational function of xi's, okay? And this formula is explicit, okay? So cluster algebra, so to construct a cluster algebra, we just, the only data we need is variable x1 to xn and one skew symmetric matrix. Then it produces certain algebra by performing mutations inductively. So sometimes it gives a finitely generated algebra, and then we call the cluster algebra is of finite type and otherwise infinite type. So this mutation, the structure of the cluster structure gives a certain n-valent graph where the vertex corresponds to C and H corresponds to mutation. So we call this graph an exchange graph. And also in skew symmetric matrix, for the skew symmetric matrix, we can always find a quiver whose adjacent matrix becomes an exchange matrix. So the information of epsilon can be replaced by a quiver. But anyway, this is an example. And the one big theorem in cluster theory is that the Laurent phenomenon, which states that if we fix an initial seed, x and epsilon, so we have n indeterminate variables. Then for any seed obtained from the sequence of mutation, then each cluster variable xi prime can be written as the Laurent polynomial in x1 to xn. So every cluster variables can be written as a Laurent polynomial for an initial seed, initial cluster variable. And the cluster algebra is a subalgebra of the field of a rational function in variable x1 to xn, generated by R cluster variables for over R seed. So this is the algebraic part. And to construct the geometric part, we take the Laurent polynomial instead of Cxs. The right-hand side gives a Cn chart, but the first Cxs to plus minus 1 gives a C star n chart. And we have a mutation formula, so rational function. So glue the spec of Cxs plus minus along mutations. Then the glued space is called the cluster variety, which is the gluing complex tori of or RC. Okay, and then Grosek and Kilcon-Savage constructed a toric degeneration of partially compactified cluster variety, but if we ignore the frozen variables, it is just a compactified cluster variety in their paper. So in our case, we apply the GHKK theorem to this situation where the cluster variety is a unipotent cell for the longest element W0 in full flag variety, and the compactified one is full flag variety. And later, so for the construction of a toric degeneration in GHKK, they do not use a Newton-Concave body. But later, Fujita Oya proved that the polytope appeared in the toric degeneration, GHKK's toric degeneration can be realized as a Newton-Concave body, and where they use the two things. They prove two things. Each seed defines a valuation on the function field, and X defines a monomers, and epsilon defines an ordering on Zn, so that we can compare the, we can put an order on the set of monomers, so we choose minimal one as a valuation. And then they also prove that for general Schubert variety, the Newton-Concave body for each valuation is isomorphic, unimodular equivalent to so-called string polytope. Okay, so right. So our sorry. Actually, it comes from the representation theory. So for actually for each height to weight measure, there is a notion of canonical basis, and then representation theorists study the parametrization of a canonical basis by certain lattice points. And actually, Littleman and Berenstein-Jelabensky found a certain polyhedral parametrization, and they call a string parametrization. Yeah. So string polytope is a convex hull of the image of a string parametrization. So that's why they call string polytope. Yes. Okay. So here's the main result. So this picture is very similar to the Harada's talks for the family of polytope. So first we start with some cluster structure. So if we have a cluster structure, then meaning that if we have a seed and we know the way of mutating seed, then we have an exchange graph. And suppose that there is a family of polytopes, which I denote by delta sub s for each seed s, such that each polytope is related by so-called tropicalized version of mutations. You know, the mutation is a rational polynomial expression, and its tropicalization becomes piecewise linear polynomial because product becomes a plus and plus becomes minimum. So every rational function is its tropicalization becomes a piecewise linear map. And then we say that the family of polytopes has a combinatorial cluster structure if they are compatible with the tropicalized mutation. Okay. So here's a proposition. Oh, sorry, I will use 2 more minutes. So here's the proposition. Suppose that we have a certain family of a polytope, which comes from a family of Newton-Cope body of a projective variety having a combinatorial cluster structure. Then we can prove that if one element, I mean one polytope is a dual Fano polytope, then all other polytopes are dual Fano. And also, if one semigroup is saturated, then other semigroups are all saturated. So this family produces seed many normal Q-Gorenstein Fano-toric degeneration. And here's the corollary. The corollary is that each seed produces a monotone Lagrangian torus in X. So, for instance, if our cluster algebra is of infinite type, then we get infinitely many monotone Lagrangian tori, but we don't know whether some of the two are equivalent or not. And also, next one is we observe the following. So the same family having a combinatorial cluster structure, and suppose that there exists a sequence of seed such that the size of exchange matrix goes to infinity, where the size of matrix means that the maximum of the absolute value of entries. And then we can prove that there are infinitely many distinct monotone Lagrangian tori. The main idea is that the size of exchange matrix contributes the number of lattice points in the dual of the Newton-Cope body. So we count the lattice point in n side. And using this theorem, we can prove that almost all full flag variety, except for this lower dimensional case, has infinitely many monotone Lagrangian tori. And we mainly use the GHK case toric degeneration and Fujitaoya and Harada-Kabe. So, okay, this is actually this picture is an interesting part, but sorry. So we translate our exchange matrix to a quiver, and then we find certain sequence of mutation such that the number of edges getting bigger and bigger and bigger. So if we proceed infinitely many times, then it goes to infinity. And then the size of the exchange matrix goes to infinity. So to analyze this, we use certain classification result of a quiver of finite type. And then, okay, thank you.